Okay, so whilst John is setting up, if anybody has any questions, please do not hesitate to pop those into the chat box. For the benefit of the recording, we're just about to show the new electrical machines add-on, Locked Rotor, for university study, and we will be providing a accessible link to this recording after this presentation. So I think we're almost set up. Do you want to share?
So I just put share screen.
Share, and then you just select the presentation. It's just there on the left, isn't it?
That one there.
Just click that and then click share. Okay. Okay, I can see the screen. Hopefully everybody else can. If you can't, shout out or give us a nudge. But hopefully John can run through this and run some demonstrations. So John, over to you.
Okay, good afternoon. Just run through these points then. What we're going to show you is how you can teach the equivalent circuits of transformers and induction motors. You can use the equipment to get or to deduce the equivalent circuit terms experimentally. I'll show you briefly the calculations and how they're made, and I'll show you some results of the modeling that we've done. We're actually using a package called GNU Octave. It's a open source free mathematical stroke modeling package, but MATLAB and GNU Octave essentially perform the same function as far as we're concerned. And this is an undergraduate product. So we start off with modeling a transformer. Essentially, we're talking about electrical machines, and as I'm sure you all know, the transformer is viewed as just another electrical machine. And a transformer is a nice place to start as far as students are concerned, because it's a relatively straightforward machine. So here you can see a pretty standard model of a transformer where we have essentially two sets of terms or two circuits, if you like, in parallel with each other. And what we do when we're modeling with a transformer is we do two tests. We do a test where we inject a AC current into the primary with no secondary load. That's called an open circuit test. And when we do that test, the parallel branch of the magnetizing reactance is the dominant term, and we assume that all the other terms in the equivalent circuit are small, so we ignore them. So by doing some relatively straightforward, simple measurements, we can deduce what XM and RM are in that circuit. Similarly, we then put a short circuit across the secondary, and in that mode, we can assume that the magnetizing reactance and the magnetizing resistance are fairly small in terms of the circuit, so we can ignore them as far as the calculations are concerned. And again, if we can measure the voltage and current, then we can deduce what the reactance and the resistance are in that circuit. Now, if I can, I'll just flip to the video.
Right, you may just want to, do you want me to do that for you?
Yeah, how do I just...
So we're actually going to get that up and you're going to explain what's on there.
I'll just show the equipment next, I think.
Right, okay, that's fine. Right, so we're just going to stop the screen share there, and just one moment, we're just going to
That's weird because I'm on your camera.
Yeah, you are, aren't you? Okay.
Oh, we're on Carl Swithenbank now.
Okay.
Hue camera, yep.
Yeah, that should be on now. Okay, we're just trying to switch into camera mode for John. You should be able to I tell you what we'll do. take that off there and pop it into mine. We'll do it in mine. Okay, we're just switching the camera over to a separate camera right now. Okay,
that's it.
So you can, hopefully everyone can see the camera now. I've got a few thumbs up and one or two have sent me a message as well. Great, okay, John.
Okay, so this is our control box, and I've got some standard 4mm connectors. And this is just a small demountable transformer set. And so with a particular sort of single phase application that we've written, we can inject a single phase into the primary, and we can measure and monitor the currents in the current and voltage in the primary when the secondary is open circuit and when it's short circuit. And we sell this demountable transformer kit. It comes with 8 coils that just sit on top of this central laminated core. So you can do lots of different experiments with that. Just to go back to this next bit of kit then, this is the Locked Rotor kit. Here we've got a 3-phase motor that is connected in a star configuration to our box. And this unit allows you to basically just, using this sort of sliding actuator there, you can either lock the rotor or you can run the rotor in open mode. There's a picture of there's a dynamometer and a 3-phase motor. And in terms of gathering the characteristics of the 3-phase motor, the dynamometer needs to be disconnected because it provides too much of a load. So we need this, we call it the Locked Rotor kit. We need this Locked Rotor kit in order to take the relevant measurements. Okay, so first of all, with the transformer, can you now see that, Liam?
No, just need to just share.
Okay, so that's the transformer. Does it take time to go through? Okay, just going through the technique then. What we need to do here is we need to measure the phase angle between the current and the voltage. So we know that the impedance of the circuit is the voltage over the current, and using a sequence here of mathematics, if we know phi, the angle between the voltage and the current, then we can deduce the magnetizing reactance and the magnetizing inductance. Ignore this picture on the left. This was last week when I had the lid off and I was fiddling about with the insides. Okay, now fortunately the software has an oscilloscope built in, and you can see here a typical plot of the voltage and the current. There's a setting on the oscilloscope where you can actually set that the x-axis is phase. So it's measuring the phase angle in degrees. So simply by measuring the peak current and the peak voltage, you can get the phase angle between the two. So here you can see in the table the results of the open circuit and the short circuit tests, and you can see there's a relatively straightforward sequence of mathematics where we can deduce what the various terms in the circuit are. Okay, I might show you the software doing that live later, but it just takes a few minutes to do it, so I've done it sort of on screen for you. Any questions on that? Just fire them to Liam.
Yeah, I'm answering a few questions in the chat, so if anyone's got any more questions specifically as we go through, pop them into the chat and I'll keep trying to answer those. I'll read them out at the end as well for the benefit of the recording. Okay.
So that's how you model a transformer. When we go on to look at the induction motor, it's really exactly the same as the transformer, apart from an additional resistance in the circuit, which corresponds to the or it's linked to the slip of the induction motor. Now, fortunately, what you can do then is you can conduct a set of identical experiments, really, where we do a free running test and we do a locked rotor test, and then we make some assumptions about the relative values in the circuit, and we're with
their microphone on. Could they mute, please? I did think I'd muted people, but if someone's joined since, it might be that the mic isn't muted. But that sounds like it's gone away. We had quite a bit of feedback.
Okay.
So hopefully that's gone. Thank you.
So yeah, fortunately then we can make these engineering assumptions about the relative values of the terms in the equivalent circuit, and by doing some practical experiments, we can then deduce what the values are. So again, on the presentation, there's a picture of our locked rotor system. There will be on the final model a plastic tube here that stops students from getting their hair or ties caught up in the mechanism. And the mathematics is very simple. We then just deduce the value of all the terms. The other assumptions we make is that the two reactances in the main circuit are equal, and that's sort of based on previous experience. Students have to accept that, and so it's possible then to deduce all the values in the equivalent circuit. Now, in terms of what we ask students to do in this package, we ask them to do the transformer equivalent, the induction equivalent, to gather the terms, and then really the main part of the package becomes, okay, now you've got those terms, now model them in a mathematical package, and then compare that model to the measured performance of the system. Now, we've done that. Did I want that? Okay. To help you do that, we've come up with an API. Now, on your screen, you can't see the detail of that, but there are about 20 or 30 commands in the API that you can issue from MATLAB or LabVIEW to easily help students to control the unit and to gather the measurements from the unit. We've had academics using this at York University with some good success recently, and we're very confident that that's quite straightforward to use. So when we've done that, then what kind of results do we get? And in front of you, you can see hopefully a graph with 3 lines on it. The blue line here, the top line, is the results that we get using the values of all the circuit equivalent circuit terms once it's been modeled, in this case in GNU Octave. The yellow line is the measured results. And so you can see, of course, there's a difference. Now that difference is down to some losses in the system, and they're losses in the dynamometer, mostly mechanical losses because of the bearings in the cradle. And currently what we're trying to do is we're trying to build a model of those losses. And the third line there is we've had a quick go at modeling the losses and actually, and then taking them into account. Clearly we've not got it quite right because that should be bang on the yellow line. So for some reason we've got too many losses in there at the moment. And there are a couple of different techniques used to model the losses, but basically you can run the dynamometer and run a DC motor separately and then try and compare the difference in terms of the current, the current and speed taken, and then you can make some allowance for it. So clearly we've got some work to do there. But actually, in terms of the main modeling, the blue line and the yellow line, they're not so different. And it's quite interesting. We talked earlier about the assumption where the two reactances in the main circuit were equal. If you try varying those, one good exercise is to get students to challenge that assumption. And it's interesting that when you do vary those by, say, 70-30 or 30-70, the difference in plot is not that great. Okay, I think that explains really. I haven't showed you the box working, but all you're going to see is a bit of software working, because you can't see the machines really.
There have been a couple of questions about whether we can see the software. Is that
okay?
Is that okay? Let me just grab your remote. I think we will need to. Right, we'll share the software environment just so that people can see that. Just give us a moment. Okay, you should be able to see that now. I know I can.
Okay, so this is the three-phase motor control software. Hopefully you can hear the machine running now. Now, when you buy this package, you actually get 6 different software applications. In terms of the three-phase one, there are 2 applications. One of those is for logging results, and the other is for using the oscilloscope to see the signals available. So just to take you through this, basically, on the left-hand side here, there's a number of LEDs which are used to allow you to check your system's okay. So there's an LED to show that the application is running, one to show that the USB is connected, one to show that the machine is plugged into the cradle properly. The cradle has a couple of micro switches, and there'll be no output unless the cradle's pushed in. One to show the direction of motion of the machine, and then another one to show you that the software is running. Along the top in blue, you can set here the frequency. You can set the driver voltage out. So the driver voltage goes from 0 to 24 volts. There's a start run button. There's a couple of switches here that universities will be interested in. We're using a bunch of very high power motor drivers to create the signals for the three-phase system. And basically, these outputs are able to go to 0 volts, to 24 volts, or to open circuit. And there's a technique called the 6-step driver system, where you're able to then change the logic, if you like, or the power output of these 3 driver systems to create a 3-phase system. And what we do is we use pulse width modulation to create a sinusoid on each of these outputs. Now, you can either have your outputs digital, so they're 120-degree phase shifted square waves, or you can have sinusoids, again at 120 degrees, or to really improve the system, you can use a system where we add third harmonics to the sinusoids, which produces a pretty perfect sinusoidal current inside the windings. If you don't do that, there's distortion on the windings. And so you can have access to control what kind of signal you're driving your system with. But in this particular case, I'm using a sinusoid, and I'm using the improved third harmonic sinusoid. Here then we've got current and voltage for each of the phases. Here I can, with the dynamometer plugged in, I can alter the loading on the dynamometer, and I can measure the dynamometer power. There's a speed here. Now bear in mind I've got the locked rotor system in, and there's no speed measurement here. The speed measurement comes with the dynamometer cradle, and there's also a torque reading there. Now on the box there's also a spare current and voltage measurement system. So here what I've got is I've got an oscilloscope. You can see the third harmonic voltage system, and you can see the sine wave current in blue. You can alter the oscilloscope to show you the true voltage signal with the third harmonics, or you can alter it to show you the effective voltage and current using this real V button here. So you can see here, there's the back EMF is that little bump there. So you can see at the moment the phase shift in a open system is minimal. Okay, do we have any questions there?
Yeah, we've got some questions. Do you want to just turn the motor
Sure, yeah.
off, and then I'll just... Okay, so just stop the motor there. There's been a couple of questions that have come through. First question is very simple for me to answer, which is, do we have a recording? And yes, we do have a recording of this meeting. We started recording from once we've done the introduction section, because we have another webinar which talks about that already available. So a recording will be provided to everyone, yes. Right, my main questions then, John, was, can we control AC motors using MATLAB, using this system?
Definitely, yes.
And yeah, the answer to that is yes. Will we get Simulink operating files with the setup, or do they need to create them using MATLAB?
They need to create those.
Okay, so those are created. This is from Asif. So those would need to be user-created files. I do know that with our system and with many products, we often provide example files, don't we? But for this system, it would be something that the user would have to create themselves.
We give a GNU Octave example in the manual. Now, that then needs copying into MATLAB. We can give the actual programs if people want them, but the idea here is that the students are going to create that file.
Okay. And then the final question, I don't know whether you'll know the answer to this. It might be that we need to ask our colleague Ben. But are all the graphical models available in the MATLAB dynamic library?
Oh, I don't know.
Right, okay, I will ask, I'll ask our colleague about that. Asif, I will ask our colleague about the availability of the graphic models in the dynamic library of MATLAB. Okay. There is another question that's come through as well, which, again, John, I'm not sure whether we know the answer immediately, but can we see the vector meter in the software?
No, there's no angle measurement system, I guess that means. There's no automatic measuring of angles.
Right, okay, so that's not available.
No.
Okay. Okay, John, do you have anything else to add to this, to the presentation at this stage? Okay. We have another question, which is it possible to perform asynchronous generator practices?
Yes, is the answer. I think there is a brushless DC motor, and you're able to drive that with a DC motor, and that gives you three-phase output, right? I think that's the answer to that question.
Okay, hopefully that answers your question, Oslinger. Okay, does anybody else have any other questions that they have? You can either ask verbally, feel free to unmute yourself, or ask us within the chat. Okay, we have another question here. If there are 20 students who have access to one machine remotely, will they need to control at different times and intervals? Yes, they would, wouldn't they?
Yes, they would.
That is probably not a suitable way of doing things. We do have a setup example where, is it using there are 6 different possible setups, is that right?
There are 6 machines, but something like 9 different wiring setups. So, for example, the DC motor is also a DC generator, but the connections are different, something like that. So if you want a full suite of remote systems, you need to set up 9 systems. If you want to do them all, you may decide not to do them all, or you may decide to do one after the other. So one day you're doing one setup, another day you're doing another setup.
Yeah. So the answer is yes, they would need to conduct at different times and different intervals, and that would need to be managed. But there is a way that we can provide a system to have one of each individual setup. Okay, do we have any more questions at all? Yeah, if anyone, if John was just saying to me there, if anyone would like to, in the coming weeks, test the remote setup, we can have a set of the machines here in our factory, in our offices in the UK. If you want to try and connect to them over the coming weeks, feel free to get in touch. I believe that you all have contact details for me now. You can always get in touch and we can set something like that up.
Hi, Lab.
Okay,
This is Joshua. Hi, Lab.
Sorry,
I'm Joshua from Yeah, I have one question for that. Actually, how you can make, is it possible to make a student assessment while they're doing an remotely, if they're triggering the mission? So how can you monitor that?
Yeah, I don't know if that's possible. The assessment here, if you like, the big part of it is, can the students construct the MATLAB file and create an equivalent circuit, and then can they take the measurements properly, if you like. So I'd have thought that was more that they were going to send you some kind of MATLAB program and you check it that way. I don't feel that an online assessment with the equipment is possible, but you might be able to think of something.
Okay, so why? Because my simple question is, if they have options for remotely triggering the machines lab, so students, we have to identify, right, to whom and where and how they are doing, how long they are doing. So whether they are completing the task within the time period, or whether the multiple mistakes, whether that how they can able to rectify that. So this would be a part of online remedy. That's why I want to know that.
At the moment, this is a very simple, just we can allow access remotely. There's no, it's just incredibly simple. There's no other, I haven't, no scheduling software. I can't provide you anything yet which sort of proves that students have logged on and done anything. It's a very straightforward system at the moment. And
then it's up to the individual users and institutions to monitor work and submissions.
But it's an interesting point, and maybe you're giving us ideas, but I would have to think about how we manage that.
Yeah. Okay.
Thank you. Thanks.
Thank you. Thank you.
Any further questions from anybody? Feel free to give us a shout. We've probably got another 5 or 10 minutes, however long anyone needs, or if everyone's asked everything, then that's also absolutely fine. In terms of cost of the system, you would just simply need to get in touch with ourselves at Matrix, and you have our contact details, or you can get in touch with our individual agents who are based in 50+ countries around the world. You can find their details on our website, or just come direct to us and we'll give you the details of your local agent so you can speak to them. The reason I say that is because pricing sometimes is something that is regional and things like that. I will be sharing the recording after we've had this. I've got that to download. There's another question just come in, but I'm not quite sure what the meaning of the question is. So you might just, Divya has just asked the question, feedback link, sir. I'm not entirely sure what you mean by that, but please feel free to build on that if you do have a question that you'd like us to answer. But I will ensure that I send you all the recording very soon. Okay, I think that we're just about done. A couple of people are dropping off the call, so I'm more than happy to call that a day. Get in touch if you've got any questions, if you'd like information on pricing, more detail, you'd like anything else sending, you'd like a specific demonstration one-to-one, then I'm more than happy to deliver those as well. Okay? Thank you, very much, and hope to speak to some of you again soon. I'll send the recording shortly. Thank you.
That's quite a few, eh?
Just let me make it. Okay, thank you.